Here are solutions to homework set number 4, ECE 320, Electronics 1. The first problem is a max-min circuit. It's given the circuit, determine which diodes are on, which ones are off. What I like doing is just kind of taking a guess. It's going to be one of the extremes. If the top diode is turned on, I'll have 8.8 plus 0.7, making this 9.5 volts. That doesn't work because 9.5 volts will turn on the second diode, and they can't both be turned on, so that doesn't work. In that case, let's assume the bottom diode is turned on. 2.9 plus 0.7, the voltage drop across the silicon diode, gives you 3.6 volts. And that works. The 8.8 volts is trying to push current backwards through this diode. It turns off. Now on the right side, I've got 3 diodes. It'll either be the maximum or the minimum. If this is turned on, it'll be 8.7 volts. 8 plus 0.7. That doesn't work because that turns on the other diodes, so that one's not turned on. Let's try the minimum. If this one's turned on, I'll have 1.4 plus 0.7, 2.1 volts, and that works. These 2 diodes turn off. I now have 3.6 and 2.1. One of these 2 diodes is turned on. If the one on the right turns on, this will be 2.8 volts, which doesn't work. I've got more than 0.7 across the left diode. So let's try the left one. If this is turned on, it's 3.6 minus 0.7, 2.9 volts, which works. 2.9, 2.1, this diode turns off. Only one diode is turned on. Once you find the voltages, I can now find the currents. 2.9 volts at 10 kilo ohms is 0.29 milliamps. 12 volts going to 3.6, 8.4 milliamps through 1K. 12 versus 2.1, 9.9 milliamps. Current has to go somewhere. There is only one diode turned on, so all 9.9 milliamps goes to diode D. The 0.29 milliamps has to come from somewhere. It comes from diode 3. So the 8.4 milliamps comes down, 0.29 splits right, and the remainder goes left. So that's the voltages and currents. If you throw this into Circuit Lab and solve, I get basically the same answers. The voltages calculated versus simulated are very close, a little bit different because diodes are not ideal. The currents are close, 8.11 versus 8.109, 9.9, 9.9, and 0.29, 0.302. The diodes that are turned off ideally have no current, and Circuit Lab says 76 picoamps, reverse flow, basically 0. So those all check out. Problem 3. This is design a clipper circuit. So if I have the blue curve, what I do is I draw in the straight lines, the orange lines, to approximate it. Kind of do a straight line if I get more than 0.5 volts off. Then I draw another line, because that's my tolerance. I want to follow this curve, give or take 0.5 volts. Once I draw the straight line approximation, I can find the circuit. The corner right here tells me this is where Zener diode turns on. One Zener turns on at 5.1 volts, the y-axis. The other Zener turns on at 8.6 volts. So when I build the circuit, this one is 5.5 volts, and this is an 8.1 volt Zener, where they turn on. To get the resistors, I look at the slope. So this has a slope of 1.5, 0.76, 0.125. It's actually 5.1 volts. What the first slope tells me is what R0 is. The initial slope here is 1.5. Tells me that R0 is 500 ohms. That's this guy right here. So the slope starts out, the slope of 1.5. The slope then drops off. That tells you R1. I've got a voltage divider times again 1.5. So the voltage divider times 1.5 is the second slope, 0.761. Solving for R1 is 1,029 ohms. The third slope slows down even more. The third slope was 0.125. That's these two in parallel. and a voltage divider times 1.5. Solving, the parallel resistance is 90 ohms, so these two together give you 90 ohms. I know that R1 is 1029 ohms. Solve for R2, 99 ohms. So there's your circuit. In Circuit Lab, if I sweep V1, I can look at the output. As V1 sweeps, I can see that the initial slope is 1.5. Then the first zener turns on right here. Then the second zener turns on right there. So that's my approximation for my curve. That's a Clipper circuit. Problem 5 is design a circuit that clips at plus 4.5 and minus 5.5. And here's one way to do it. This is something small. What I want is V2 to equal V1 when the zeners are turned off. By voltage division, it's not quite the same. This is, I'm 99.9% of the same. This first zener turns on at not quite 4.5, 4.5 minus 0.7. The reason being is this is a diode. When it turns on, I've got a 0.7 volt drop across it. This one down here is a 4.8 zener, which is our 5.5 volt zener, minus 0.7. Gives you 4.8 volt zener. If I then try that in Circuit Lab, have V1 sweep going from minus 9 volts to plus 9 volts, I can see the first one turns on at 4.5 volts. The second one turns on at 5.5 volts. So that works. Problem 6 is a transistor circuit. Or here's a transistor. Label the regions. Right here is the active region. In the active region, IC is the gain times IB. Depending upon the textbook, is either beta IB or some textbooks use HFE. That's what DigiKey uses, HFE. It's the gain from the base current to the collector current. To find out what the gain is, just take the ratio. 5 milliamps produces 100, 20 to 1 ratio. 4 produces 80, 3 produces 60. Always 20 to 1. So that tells you the transconductance gain is 20. Let's see. The load line then is if the current is 0, I have 10 volts across the transistor. So I intercept the x-axis right here at 10 volts. On the y-axis, if I short this, I get 10 volts over 100 ohms, 100 milliamps. 2 points determines a line. There's your load line. And the regions are down here. This is the off region when the current is 0. This is saturated when we assume the voltage is roughly 0.2. It's close to 0, but not quite. And the active region. In the active region, the voltage collector to emitter is less than 10, bigger than 0.2. The last problem says, okay, now draw the load line and calculate the Q point when Vn is 0, 3, and 6 volts. At 0 volts, that's easy. Everything's 0, the currents are all 0, and VCE is 10. At 3 volts, I know that the base current is 3 minus 0.7, the voltage drop across the silicon diode, 2.3 milliamps. IC is beta IB, 46 milliamps, and then the voltage is your 10 volts minus IC times RC, 5.4 volts. And at 6 volts, if I assume active, I have 5.3 milliamps at IB. IC will be beta IB, 106 milliamps. That doesn't work because again, VCE is negative. Negative voltage tells you that it actually saturates. VC can't go negative. If it did, it'd produce energy. And it can't even quite get to 0. So we assume it's like 0.2. Close to 0, but not quite. In which case that's IC. Points are right here. When Vn is 0, I'm off. 3 volts, I'm active. And 6 volts, I'm trying to operate up here on the dotted line. I can't get there, so I saturate. I move up the load line as far as I can to about 0.2 volts. Then I'm stuck. I'm saturated. The last part is to build the circuit in lab, take the measurements. For the currents, you typically have to calculate the currents. If I know RB, I can measure the voltage at the base, I can measure the voltage at the collector, and calculate what is IB. That's your 5 volts minus VB, about 0.7, over RB. Calculate IB. VC, I can measure the current is your power supply minus VCE over the collector resistor. The ratio is the current gain. And if you plot those operating points, oddly enough, they all fall on the load line right here. This is when IB equals 0. As IB increases, I move up the load line, and I try to go left of the x-axis, but I can't. I saturate at about 0.2 volts. Homework set number 4 for ECE 320.